Hello everyone, my name is William Wolf and I'm based at the University of Oxford. Today I'm going to be talking a little bit about the current status of single scalar field dark energy, particularly in light of some of the recent results from the DESI collaboration. This work is done in collaboration with Pedro Ferreira and Carlos Garcia. We've written a series of papers on this topic, but we also have some new results that I'll be talking about in this talk that should be on the archive within a couple of weeks. We've all seen some version of this plot, so this is showing the current constraints on the dark energy equation of state coming from the DESI collaboration under a few different data combinations. And what you see here is that there's a pretty robust preference for dynamical dark energy over what we would expect in a ΛCDM universe. So these constraints are typically obtained by assuming that dark energy takes a parametric form, where W0 is the value of the equation of state today, and WA captures any time variation. One of the really curious things about looking at this plot are the positions of these constraints on W0 and WA. So if you look at W0, you could see that clearly the lambda value of -1 is disfavored, but dark energy hasn't evolved very far past that value, so it's still pretty close to -1. However, if you look at WA, the value of WA is very large and negative, which can be indicative of significant temporal evolution. And as we'll see here, it can be difficult to reconcile both of these constraints simultaneously when it comes to actually building a microphysical model of dark energy. So, what are our options here? Well, the simplest thing we can do is we can consider a single scalar field and add it to our cosmological equations. This scalar field can have a potential energy, a kinetic energy, and possibly other couplings between gravity or matter fields. And here in this talk, we're going to consider three distinct possibilities. The first one is that dark energy is driven by quintessence, and this would be when it's minimally coupled to gravity and it has a canonical kinetic term. So this is the most familiar form of dynamical dark energy. We can also introduce a non-minimal coupling into this model. This is both going to change the strength of gravity as well as introduce additional terms into the pressure and energy density of the scalar field. And this is going to allow for the dark energy to have a greater variety in terms of the phenomenology for its equation of state. So here you can actually dip into the phantom regime, so you can go below -1 and then cross the phantom divide when the potential takes over, and then it starts looking a little bit more like typical quintessence. And then finally, we can also keep the coupling to gravity minimal, but then introduce modifications or make the kinetic sector a little bit more general by introducing a generic coefficient alpha and the box phi term. So these types of theories are most familiar from the Galilean literature, and those models are pretty well known because they have a shift symmetry and they allow for self-accelerating solutions for the cosmos that allow for accelerated expansion even in the absence of a cosmological constant or a potential. However, those theories are a poor description of the current data because they remain in the phantom regime throughout their episode. So here we'll keep the box phi term, but we'll allow for the shift symmetry to be broken by including the potential. And these are going to have very similar phenomenology in their equation of state when compared with the non-minimally coupled models, even though they modify the strength of gravity differently. So then what we have to do here is, for all of these different choices, we have to specify a potential function. Now, in the literature, there's been a lot of different potentials considered: exponentials, axions, quartic potentials, and all sorts of other forms. Here we're going to consider a Taylor expansion of the potential. So the dark energy scalar field is frozen throughout most of cosmic history by Hubble friction and only really becomes dynamically relevant at fairly recent times. So generally speaking, with dark energy scalar field models, the field excursion will be pretty small. Right when you look at a scalar field potential like this is actually going to be a very good approximation of a huge number of other potentials that have been considered in the literature. And here's an example of this. So just consider the axion, take a Taylor expansion and keep the first two terms, solve the cosmological equations for both, And what you find is that the field excursion for this model is very small. And from a equals 0 to a equals 1, over this range of field excursions, the potentials are indistinguishable by eye. And the actual predictions for different observables are the cosmological data will not be sufficient or able to discriminate between these. So just by taking the Taylor expansion for all of these dark energy models, you can cover a huge variety of distinct potentials and behaviors. So now the question becomes, how do we decide whether one of these different types of building a single scalar field model is a good description of the data or a bad description of the data? So what we need to do is we need to determine the theory priors in the W0 WA space. If there's overlap between the data and the theory, you have a good theory. If you don't have any overlap, theory is probably not a very good description of the data. Simple enough, but there's actually a huge number of ways that people have actually considered determining the priors in W0 WA space for these dark energy models. So here's just a couple examples. So sometimes people will just take the derivative of the equation of state at a certain point in time. Other times people will fit a model of W0 WA to a dark energy model's theory curve for the Hubble parameter over some range of redshifts. Or what you can do is you can actually fit W0 WA to the predictions for H of Z at the specific redshifts and using the errors of whatever data set you're considering. But all of these give distinct predictions for a dark energy model's representation in the W0 WA space. So here, how we've gone about doing this is we've sampled across a wide range of our dark energy model parameters, and then when we do that, we generate predictions for the exact observables that are probed in experiments like DESI or the CMB and supernova surveys. And so that's going to be things like the Hubble rate, the angular diameter distance, etc. And so then what we do is we generate the exact observables that are probed. So this will be the exact predictions that these models give for those observables. And then we fit a model of W0 WA to those observables using the errors of the actual data. And what this is going to do is this is going to give us a nice apples to apples comparison where we can compare whether or not any of these dark energy models have overlap with the constraints on the actual data that give us these posteriors on W0 WA. So it turns out when you do this and you project these theory priors into the W0 WA plane, what you find is that, unsurprisingly, all of these different dark energy models are a better description of the data than ΛCDM, but minimal quintessence does not have a very large overlap. The data has most of its constraining power at these intermediate redshifts, and if you have a model that's starting from W equals -1, if you have significant temporal evolution in those intermediate redshifts starting from W equals -1, well, it's going to be really easy for you to overshoot the constraints on W0. In comparison, when you have these models that allow for more general behavior in the equation of state, the ones that can dip into the phantom regime and then cross the phantom divide, totally different ballgame where they can, even within these intermediate redshift ranges, you can still generate significant temporal evolution evolving from below -1 to across the phantom divide without overshooting what the constraints on W0 are right now. So this is an exercise in determining the theory priors for all of these different models of dark energy, or rather these different ways of building distinct single scalar field models of dark energy. And this is going to give us an idea of which ones are going to be the best descriptions of the data. And so now we're going to turn to the full data set. So when you do this, these results line up with exactly what you would expect based on the previous slide. So all of the dark energy models, minimally coupled, non-minimally coupled, the massive Galilean, the W0 WA models, all of them fit the data better than ΛCDM. However, the ways in which they fit the data better line up with exactly what we'd expect. of the dynamical dark energy models, minimal quintessence is by far the worst description of the data in terms of its ability to fit it. And then the more exotic scalar field models are on par with or even a little bit better than the W0 WA model. And we'd expect them to be on par given that their theory priors share significant overlaps with the data constraints. And one of the really interesting things here is looking at the comparison between the DES DR2 and the DES-Dovekie results for the evidence for dynamical dark energy. So DES DR2 is the supernova data set that has been giving the strongest preference for dynamical dark energy. And then when you go down, you can look at the chi-squared numbers for these different dark energy models. But even when you impose additional penalties, statistical penalties for introducing new parameters, the cosmological evidence, whether you're looking at the delta AIC or the Bayesian evidence, still show a strong or even overwhelming preference for dynamical dark energy. However, there was a recent recalibration of this data set that's given by the DES-Dovekie likelihood, and this reduces the overall preference for dynamical dark energy. And we can see that that has a pretty substantial impact on our inference regarding the statistical evidence for some of these more exotic dark energy models. So when you go from DES DR2 to DES-Dovekie, you go from inferring very strong or even overwhelming evidence for some of these models to only showing a moderate preference for them. And then in the case of thawing quintessence, you go from seeing a moderate preference for it over lambda CDM to it being effectively statistically indistinguishable. So both Galileans and non-minimally coupled models are going to modify gravity on cosmological scales. So in this case, you're going to modify the Newton-Poisson equation, and you'll have your potential phi that affects matter being determined by mu, and then the gravitational potential that affects light rays given by sigma. And so in GR, both of these values are equal to 1. And you can see here that when you're only considering the cosmological data relevant to the expansion history of the universe, both of these are going to favor a mu and a sigma that deviate quite substantially from their GR values, especially at low redshifts. So we can look to the growth of structure data. You can see here that both the non-minimally coupled and the massive Galilean models are going to deviate from the predictions for the growth of structure that you would expect from lambda CDM. However, when you look at the actual constraints on F sigma 8 that come from the previous BOSS survey or the current DESI DR1 release, the error bars are still pretty large and they're not actually that discriminatory. However, there are other ways of measuring F sigma 8. So, for example, the data point at z equals 0 comes from measuring peculiar velocities, and you can actually get really high quality tight constraints on F sigma 8 from these measurements. And they're, as we're about to see, they can be more discriminatory than some of the intermediate redshift measurements. In this case, what we did was we combined the CMB and F sigma 8 data for both BOSS and this low redshift measurement using peculiar velocities, and we compared the constraints on the Xi and alpha parameters with those you get from just looking at the expansion history data. And they show something really interesting. So in the case of the non-minimally coupled model, well, and actually in the case of both of these models, so Xi measures the strength of the magnitude of your non-minimal coupling to gravity, and alpha measures how non-canonical your kinetic term is. And so, just looking at the CMB plus BOSS F sigma 8 data, the constraints on Xi and alpha remain consistent with what you get when you do the full complement of expansion history data. So not much different there. However, that single low redshift F sigma 8 data point, when combined with the CMB data, is going to immediately pull the Xi parameter back to back to 0, and so this data is going to pull this model back towards minimally coupled quintessence. And then the same thing with the massive Galilean model. The constraints here are going to pull you away from the wrong sign kinetic term, so a negative alpha, and back to the canonical values you'd expect from a single scalar field. or that is minimally coupled to gravity and that has a canonical kinetic term. And so this highlights the importance and the potential discriminatory power of growth of structure measurements, particularly those that are at low redshift. Now, the constraints on F sigma 8 coming from stage 4 surveys like DESI and Euclid are expected to get a lot better in the coming years, and they'll give much tighter constraints on F sigma 8 measurements. However, these surveys are going to have most of their constraining power in this intermediate redshift range. So while that will still be very informative, there's definitely going to be a place for high quality, low redshift measurements of F sigma 8, because this is exactly the regime where these dark energy theories are going to be most different from each other and from lambda CDM. So now let's talk about the integrated Sachs-Wolf effect. So this is basically measuring the cross-correlation of large-scale CMB anisotropies with tracers of large-scale structure. And so what this is effectively doing is this is going to probe the time variation of the gravitational potential on the largest scales. So just considering minimally coupled quintessence for a second here, the time derivative of sigma here is going to, of course, be 0 because this is not a modified gravity model. And so the time derivative of the potential is going to be negative in this case. However, when you introduce these modifications to gravity, that's going to have the potential to both enhance F sigma 8 as well as increase the strength of gravity. And so given that, it's possible to actually flip the sign of this. Coming to the actual data, we can see here that minimally coupled quintessence is clearly closest to the integrated Sachs-Wolf data, and that's also going to give very similar predictions to lambda CDM. And then at the complete opposite end of the spectrum, you see the cubic Galilean. It's well known that this has a pretty significant tension with the ISW, and again, that's because it's purely modified gravity effects that are driving that result without any kind of scalar field potential. But then when you come to the non-minimally coupled scalar field model and the massive Galilean model with the potential, you end up somewhere in the middle where you have the effects of a decaying gravitational potential from the scalar field potential and the effects of modified gravity that are competing with each other. So these are still preliminary results and they haven't been finalized yet, but we expect a somewhat of a tension between the ISW and these modified gravity models, but nothing quite as definitive as what you see in the cubic Galilean case. So in summary, the cosmological data, and more specifically the cosmological data with respect to the expansion history of the universe, clearly favors dynamical dark energy over lambda CDM. Now, the extent of this preference is a little bit model and data dependent. However, the preference is there and it's fairly robust. Now, some other big takeaway here is that scalar field models with exotic couplings that allow for phantom crossing, such as those we've seen with the non-minimally coupled model or the massive Galilean model, clearly outperform quintessence across the board. However, these models also introduce severe ancillary gravitational consequences through modifying the strength of gravity, and this is going to affect other measurements such as those we see in the growth of structure or in the ISW. And it's clear that even if the data right now doesn't offer super strong discriminatory power, there's definitely the potential for it to do so in the future. So this is something to look out for. And then finally, everything we've done today was done with just a simple Taylor expansion of the potential. And this is a justified approximation because, generally speaking, these field excursions for scalar field dark energy models are going to be fairly small. And so simply Taylor expanding the potential is going to be degenerate with a lot of the other forms that we've seen in the literature. Cosmological data will tell us a lot about dark energy. It has the potential to tell us whether it is changing in time. It has the potential to tell us whether there are any kind of exotic features or couplings that modify gravity. However, it's very unlikely that cosmological data will ever get to the point where it can offer super strong discriminatory power with respect to the form of the scalar field potential. That's my talk, and thank you so much for the organizers for inviting me to speak at Dark Energy from Home, and I'm now open to questions.